Okay, welcome you to the second video on circular motion. Now we're talking about when the body moves in a circle. It could move with a constant speed or with a non-constant speed. But this case, or the last video, I said this body moves with a constant speed. The speed is constant in magnitude. Let's call the speed V. Remember that speed is a scalar quantity, does not have direction. So here it moves from point A to point B with the same speed V. But the velocity is not the same because velocity is a combination of the speed of a body and its direction. So since the direction of the body at A, and I said in the last video that the direction of the body at any point is the direction along the tangent at that point. So because the direction at point A is not the same as the direction of the body at point B, it means that the velocity of the body at point A, let's call that VA, is different from the velocity of the body at point B. Let's call that VB. And I said in this case, though the body moves with a constant speed, constant in magnitude, the velocity is not constant, it keeps changing. And because of that, the body accelerates. And I showed you how to find the change in velocity and all that. Now, here we are going to look at, we continue from there. We're going to look at angular velocity of the body. Angular velocity. Now, the symbol is omega, the symbol of angular velocity. And how do we define that? Recall that when the body moves from point A to point B, it is swept through an angle theta. And this theta is measured in radian. And theta is defined as the angular displacement of the body. And the direction is outward or along the center of the circle. Now, angular velocity is defined as the angular displacement covered, angular displacement turned through by the body per unit time. Angular velocity is angular displacement discovered or turned through per unit time, and it is measured in radian per second. Angular displacement is in radian, while time is measured in second. All right, so this angular velocity has a direction because it's also a vector quantity. The direction is the same as the direction of angular displacement. It is through the center of the circle, so it's also an axial component. Okay, so that is the angular velocity of the body, defined as the angular displacement divided by the time. Now, there's a relationship between, let's look at how they are related, relationship between the linear velocity or linear speed of the body, the angular velocity of the body, and the radius of the circular track. Now from the two expressions, I'm going to write three equations rather. Now the angular displacement is also defined as the linear distance covered, which is the arc length. Distance moved from point A to point B along this arc divided by the radius, and that the linear speed is linear distance over time, and that the angular velocity is angular displacement over time. Okay, I'll start with equation 1, that is this is equal to this angular distance over radius, and then dividing by time t. Dividing this equation 1 by time t, I'm going to have here this over this gives me s over t multiplied by r. Now this theta over time t, of course is the angular displacement, is the angular velocity. And this is my linear velocity, distance over time, that's my v. Remember that this r is a denominator over this. So when I cross multiply, I'm going to have that the linear speed is equal to angular velocity multiplied by the radius of the circle. So this gives a relationship between the linear speed and angular speed. Angular acceleration. Angular acceleration. Now the symbol is this. We call that alpha. Angular acceleration is defined as the angular velocity turned through per unit time. So we can call that angular velocity divided by time. That gives me the angular acceleration. And this will be measured in radian per second squared. That gives the unit of angular acceleration. Now, we can also define angular acceleration in calculus as uh, the rate of change the, of the angular velocity with respect to what? To time. Okay, and in terms of angular displacement, it can also be given as the second derivative of the change in the angular displacement over the t squared. Okay, now we can do a very fast comparison between angular acceleration and angular speed. Let's do some comparison. Angular acceleration, can we compare that to linear acceleration? Linear acceleration. Okay, so this is the symbol of this is alpha, this is just a. Now we know that this one is defined as change in this over change in time, while this is given as change in velocity, linear velocity over change in time, that is linear acceleration. We also know that angular acceleration is given by the squared times angular displacement over the time t squared, the t squared, while this is given as the squared of linear displacement over the square of the t squared in calculus notation. Then, of course, you know that this is given by the change dw, change in this over change in time, which is also given as, I want to now write down in terms of angular displacement and angular velocity. We can split this into the theta over the t times the omega over the theta. Okay, this is the same thing because you look at this carefully, it's a product. This tends to cancel out this, giving you back your d omega over the t. So which means angular acceleration is the same thing. This gives you your omega, which is your angular velocity multiplied by the omega over the theta. So this is another expression for angular what? Acceleration. And then for linear acceleration, you can do same here. That gives you A equals V times dV over dx. Okay, so now for constant angular acceleration, the equations of motion will also apply here. Just like in the case of a body moving along a straight line, when it moves with a constant acceleration, we can use the equations of motion to calculate the parameters of the motion of a body. One of them is a final velocity v equals u plus at and so on. So the same thing applies when the body moves around a circle with a constant angular acceleration. So we're going to place the two equations side by side. Let me move to a different sheet. Now, here I can say for angular acceleration, this is angular acceleration, okay, and this is linear acceleration, okay. This is what we commonly call acceleration in linear motion. Now, the first equation for this is final velocity equals initial plus acceleration linear multiplied by the time t. Here is going to be, I'm going to use omega as my final angular velocity equals to omega naught. This becomes the initial angular velocity plus angular acceleration multiplied by time t. It applies because we are looking at the case where this body, as it moves in a circle, it moves with a constant angular acceleration. So the first equation applies, quite similar to that of equations of a body along a straight line. So the second equation, I'm going to use theta as my, angular displacement. Here we have angular linear displacement equals ut plus half at squared. You can write same using angular acceleration. This is the distance covered equals omega naught t. Of course, this u is like my omega naught, which is initial angular displacement, half angular acceleration times t squared. Sorry, there's a squared here. All right, so the next equation is v, that is v squared equals u squared plus 2as. I can say the same thing here. Omega squared equals omega naught squared plus 2a alpha times theta. The other one is, average speed. Total distance covered is average speed or velocity multiplied by time t. You can do same here, that angular displacement covered is given by what? We have, this is this final angular displacement over this divided by 2 multiplied by time t. So all these equations apply. So by next video, we will start solving problems using these parameters.